Good afternoon, good morning, good evening, everybody. I hope you're doing all right. This is Ian Coates, your instructor here for Math 1031. Welcome to week 9. It is summer 26, and I hope you guys are having a great summer. This is the week 9 material, and this will conclude everything there that will be on the test there for next week. So lots of fun, and this is where we're getting into the nitty gritty there. We basically only got about 5 more weeks to go, and yeah, lots of fun. So you'll need this information there to complete your assignment 2 that is currently out and live as well. You'll need this there for the test there that'll open up there next week. You have lots of time, no stress, just putter away at it and away you go. Today we're going to finish up their measures of position. The last week there and the previous week we looked at mean, median, mode. We introduced standard deviation and the whole idea of what variance is and dealing with the spread of the data. We're going to take that a little step further there, and we'll show you guys some interesting stuff there today as well. I put this right here on the title slide just to kind of, you'll see there that we have data set A and data set B. And you know what I mean, just a quick glance, I got 10, 20, 33, okay, I got 100. So there are, I can just quickly see there are some differences, but they generally kind of look the same. You know, there's some small variances here or there, but they have very similar qualities, these two data sets. And if you have a look here, that they actually do. They both have the same mean, 55. They both have the same median, which is 55, and they even have the same range, right? 90, 100 minus 10, right? So there are a lot of similarities, but I wonder what these two populations do look like. Are there any differences, measurable differences? We'll come back to this there. Okay, I just wanted to show that to you there. This is what is covered there for the next test, right? We did that there week 7, 3.2 there. We did last week, week 8. And here we are there this week, 3.4 measures of position. Okay? Off topic, but not really. I just wanted to tell you guys there, be careful of rounding, okay? Never, ever, ever round until the end. And you're going to see some procedures there today that I really don't want you to round, okay? Like this example here, 8.453. It is equal to 8.453, not 8.5, okay? Rounding that would there, you know what I mean? Round that up. Yeah, you could. They're very similar, but they are not the same. And I want you guys to carry a couple of decimal places there on the assignment, and I'll show you where. Okay, the quiz. All right. Do not round, and if you have to round, do it at the very end. Okay. I do not mind if you carry a couple of decimal places in your answer, okay? So you have a look here, 4.532 plus 6.500, that equals 11.032, okay? You just don't round, okay? Here I've got 72.6, 75.6, 74.6, 86.6, 80.6, and 82.6. Not rounded there. The mean is 78.7666. Okay. If you do round, you know, you can round this there to 78.8. But what if we rounded these already before I did my mean? What if I made that 73, 76, 75, 87, 81, and 83? My mean would be completely off. So these numbers here, you never round them. Don't round anything until the end. I don't mind if you keep a couple of decimal places hanging out. Okay? It's just good for the nature of the business here. and I'll show you why there in a little bit. So all of this is a go there for test 2, okay, week 10. We've looked at measures of dispersion or variation. There's your measures of position and range, quartiles, range, and interquartile range. We're going to talk about these there today. We talked about these there last week and previous. Okay, let's go. So compare the two data sets, then analyze. You're not going to do that right now, but we are going to come back to this. Okay, this is from the title slide again, right? You have your two data points, two data sets there. They look very similar, but they are not the same. How are they different? Are the people in these two data sets thinking alike? Well, at first glance, both have a mean of 55, both have a median of 55. The range is 90. Like, you know what I mean? It appears that these two are very, very, very similar, if not the same. Okay? And just, I don't know, I always like to tinker with my slides there, but you have a look here. The summary statistics seem to imply that the data sets are identical, right? Same mean, same median, same range. However, we know that this is incorrect. And we'll have a look at these, and we're going to break these two down, and I'm going to show you how different they really are. Okay? And all of this information is relevant, and because, as I've said many times there, the whole idea of statistics, right, is you're going to do a sample of a population that you don't know anything about, and you're going to project the information from your sample onto the entire population, right? There's a whole lots of things there that we, and everything there that we're doing, you know, you're able there to turn the mashed potatoes into, you know, some type of usable information, right? Clarifying it all up. Okay, let's go. So, introducing quartiles and percentiles. Okay, the first quartile, or what we call the lower quartile, is the point below which the first quartile, or basically it's the 25% range. Okay, so your first quartile, like just looking at these two data sets again there, your first quartile is the 25th percent, the way up the scale. Your second quartile, also known as the median, so if you found the median, then you have actually found the middle of the data, which is the second quartile, 50%, right? 50% here, 50% there, that's your median, right? The third quartile, Q3, what we call the upper quartile, that is your 75th percent, okay? And what data value corresponds to the Q1, Q2, Q3, these kinds of things here. So, identifying percentiles in a data set. Okay, this formula right here, you may have seen there before, location of the K percentile. So you have a look here. LK is the location or position of the corresponding data value in the array, right? The array is ordered from lowest to highest. That's what an array is. So LK is the location or position of the corresponding data value for that particular percent. K is the desired percent. Is it the 25th percentile, the 50th percentile, even the 67th percentile? Anything from 1 to 100, that's percent, right? So K is your percent. And then N is the total number of data values in the set. So if you got 10 data values in the set, then that would be 10 plus 1. And how to use this formula there, we look at there the next slide. Okay, so just getting into the quartiles, what they mean, right? There's your first quartile. There's Q2, which is also your median. And then what number correlates there? What data point correlates to the 75th percentile? Okay. Now, percentiles here, we use them all the time. I'm sure you guys have seen these. I use them there. These are, I've downloaded these. I use these there for my kids. The whole idea, percentile growth charts there for boys and girls, right? And you'll see there that when you're talking about, there's height and weight on all of these. So weight, right? So these are the weights there of children across Canada, right? And so you have the 50th percentile, the 25th percentile, the 10th percentile, 75th, 90, 95th percentile. So the middle of the road child, the child there that has the 50% at, the average weight for most kids here in Canada, they would be on the 50th percentile. Okay? If your kid is heavier than the average child, then they'll be up into this range here. Okay? Works the same there for height, right? There's your 50th percentile for height. If your child is a little shorter than the average child, then they may be down in this range. Okay? Down less than the class average. So this 50th percentile is basically the class average. Okay? So that's what we're talking about there with percentiles. So in this case here, find the location of the 10th, find the location of 10% of the data. And this is denoted there as P subscript 10. So that's basically your 10th percentile, right? And just going into the slide here, I'll just go over to the girls here. And yeah, you'll see there, basically what we're finding there, the question there from the PowerPoint is asking us to find the 10th percentile. Okay, so there's going to be 90% of the data is going to be above these points right here, right? So just getting into this, find the location of 10% of the data, the lowest 10%, P10, using this formula right here. And you can flip this formula around, like right now this formula is in terms of LK, and that is your location, all right? LK is the location or position of the corresponding data value in that array, okay? So this formula here is written in terms of LK, but I can come also flip this there and write it in terms of K. And you remember there, K is your percent. So now this formula, same formula, is written in terms of percent. Okay, so here is just another set of data points there, unrelated. It doesn't matter. Okay, and you'll see there that they are all ordered. 60, 60, 62, 63, 65, and you see how it's all increasing in order all the way up to 80. I'm looking for the location of P10. So LK is equal to 10, right? Because that came from here. So that's got to be 10 over 100, right? And that's what we've got. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 numbers in total. So that goes in there for N. So 12 plus 1. All right, so there's your 13. And if you 10 divided by 100, which is 0.1, times 13, you get 1.3. So that is the location of P10. What does that mean? All right, 1.3. Okay, so if LK is a whole number or less than 0.1 away from a whole number, then stay. If LK is a decimal between 0.1 and 0.9, take the mean of those two numbers. Below 5 goes down, above 5 goes up. Blah, blah, blah. What in God's green earth does all that mean? This is what you want to know. Okay? Example, if LK is 12.4. So if you, and basically what you're talking about here, what this number means is it's 1.3 up. And I'm just going to go, let's see here. You have a look here. So 10% of the data lies within 1.3. So in this range right here, this is 10% of the data. But wait a second, we've got these two numbers here. 0.3 falls in between two numbers, right? Because that's what we're trying to find the location of the 10% of all data points, right? So in this case here, 1.3, I'm in between these two numbers. I add these two up and divide by 2, and 60 divided by 2 is still going to be 60. So therefore, approximately 10% of the data falls below 60. Okay? And this 60 here. So, and again, if LK is equal to 12.4, take the average, and you see what this is telling you here is that this particular percentage, just like this one here, falls in between data values, right? Because this is telling you there that it's the first position plus a little extra. The first position plus a little extra. Okay? So that's why you have to do this. Let's say you get an LK value of 12.4. You get a decimal again, just like we did here. So that's telling you there that it's the 12th position, just above the 12th position, somewhere between the 12th and 13th position. That's why you would take the average of the 12th and 13th data value. And you add those up, divide by 2 as we just did in the example, and you will get the particular LK position value. Okay? There's that slide there showing you guys all the different percentiles. Okay? Here's some more examples here. Same thing. Using the data points there that we were using earlier. Okay? And I want you guys to find the P10, which we already have. P25, so we want to find the 25th percentile, the 67th percentile, and the 90th percentile. And what I've done is I've got them all here. Everything's all ready to go, showing you guys how to do these, and just showing you there according to the formula and where everything is. You'll see there that there is your P10, there is your P25, there is your P67, that's your 67th percentile, and then there is your 90th percentile, right? And somewhere in here I would assume would be your median. There's your P50. But we just did this one here for doing P10. Oh, sorry. Right? And there's your 10 divided by 100. 12 plus 1 is 13. 0.1 times 13 is 1.3. Divide by 2. And you get a P10 value of 60. Let's have a look at P25. They're donated in green. Okay, so location of P25, there's your 25% over 100, still dealing with 12 numbers plus 1. So you get a number there of 3.25. So moving up 1, 2, 3. So somewhere between 3 and 4, right? Because that's 3.25. Right? So we're in there somewhere. So I need to take 62 and 63 and divide by 2, which is what is happening here. So at the 25% of the 25% of all data falls below 62.5. Let's have a look at P67. Right? Here we go, 67 divided by 100 times 13. And here we've got 8.71 positions up. So 1, 2, 3, 4, 5, 6, 7, 8. So it's 8.71. So it's in between these two numbers, 68 and 70, which is why I add those up, divide by 2, and I get a P67 value of 69. Okay. P90. Again, same thing here, 90 over 100 times 13 is 11.7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's in between these two. 77 plus 80 divided by 2 gives me a number there of 78.5. You know, and this is just rough. It's not exact science. It just gives you an idea. It points you in the right direction. Okay. Find the range of the following data sets. Okay. Here I've given you the data sets there, and I've given you the answers there. The whole idea, the range is your highest number. 86.1. It's not an array. Minus 72.9 gives me a range of 13.2. Calculate the first and third quartile for the following data set. So you're looking to find these guys here, right? Okay, so you're going to find Q1 and Q3. Okay, as well, and there's your median there as well. Okay, let me know if you guys have any issues or if there's any errors or anything like that, but we should be good to go. Okay, so try these out, confirm, practice, away you go. All right, so let us move on, shall we? The whole idea here, measures of deviation, this is the MAD, okay? The deviations from the mean, and this is where we're going to be focusing, okay? The whole idea here is this is your data value minus the mean, and deviations of the mean. One way to measure the differences present in two data sets is to calculate the measure of deviation, okay, which analyzes the spread between the individual data values in the set and the mean. How far away are these data points from the central axis, the mean, right? So here we've got, okay, calculate the deviation from the mean in the sample set. So here we've got a small sample set. And generally that's how things will go on a testing situation. I think on the assignment there's one question there. It's got a whole whack load, calculate mean, median, mode. But you'll see that, you see how things are here. We're going to be getting into this whole, I'm just going to try and move ahead. Things like this. And, all these different data points here. I will be asking you to do chart filling in exactly like this, but I would never give you, 15, 20 data points. It just becomes boring and repetitious, and these can be quite intricate as well. So just letting you know that you'll see that I usually give small data sets there on a testing situation, okay? Looking for accuracy, looking for correctness rather than, repetition kind of a thing. So for the following data set, calculate the mean absolute deviation from the mean, okay? So here I got 55, 65, 70, 72, and 78. So calculate the mean, and we found there you add them all up, divide by 5, okay? You get a mean of 68. All right, so you take these numbers here and you fill them in here in order. And then you'll see there that this is for the mean. The mean is the same for all data points. So you just put in 68 all the way down. Okay? Now you'll see that what we're dealing with here, this is the data point minus the mean. How far is that data point away from the mean? So in this case here, 55, and it's the number minus the mean. It ain't ever the mean minus the number. You're going to get negatives and positives here. It's part of the ball game. You just got to keep them organized. Okay? So 55 minus 68 is negative 13. 65 minus 63 is negative 3. 70 minus 68 is 2. 72 minus 68 is 4. 78 minus 68 is 10. A little self-check to let you know that you have done this step correctly is if you add them all up, it always equals 0. 10 plus 4 plus 2 is 16. Negative 13 and negative 3 is negative 16. Negative 16, positive 16 is 0. Good. That one's good. Now we take the absolute value of those guys there, and it just means get rid of the negatives. Okay? So the distance there between the data point and the mean is 13. And this is telling us there it's in the negative direction. We'll get more into that as we go. So you just take the absolute values of these and then you sum them. There's that Greek symbol, means sum. You add them all up, you get 32. So the mean absolute deviation from the mean there, also called the MAD in this case here, okay, is 32. divided by n, which in this case here, the average distance from the mean, according there to the MAD there, is 6.4. And therefore the mean absolute deviation of the data from the mean is 6.4, which tells us that the average distance between a data value and the mean is 6.4. So there is some space, generally speaking, between the mean of the data and the average data point. Okay? We'll come back to that there. Here we go. Variance, distance from the mean, or spread of data. Okay? And I'm just going to send that back there. There we go. So now we start getting into the big banana kind of a thing here. The variance is the mean of the squared deviation. Okay, there from each data value to the mean. So remember this guy here? Okay, we're going to take this information and we're going to transform it into the variance. And then the variance, we're going to transform that into the standard deviation. Because ultimately what we want in statistics, you need that standard deviation. Okay, so just again, the variance is the mean of the squared deviation from each data value to the mean, what we just calculated there. Squaring makes all the deviation values positive and is a convenient way of overcoming and canceling out effect, and is more commonly used in statistics than the MAD. Okay, we do use the MAD. It's not a huge part of the course. It's just kind of a stepping stone to get to where we need to. The variance and the squared and the standard deviation, that's what we really want. Okay. Like the MAD, variance increases the more spread out the data values are, and is a better measure of dispersion than the range, as it uses every value in a data set. However, unlike the MAD, which is a descriptive statistic used for sample data sets, the variance is more of an inferential statistic. This is the one we want. Okay? And so the method of calculating it depends on whether the data set constitutes a population or a sample. Okay? This is where we want to be, people. So, excuse me. The variance is the mean of the squared deviations from each data value to the mean. And there's two formulas here. This is where we're going to be kind of hanging out, okay? Because here we're talking about variance of a sample, okay? The variance of a sample is represented there by the symbol S squared. The population variance is theta squared, okay? But you'll see there that there's your sum of x minus the mean squared. We just did that up here, right? X minus the mean. We didn't square it yet, but that's why we don't use the MAD that much. I'm just showing it there to get us to where we need to go. Okay. This is the variance there for a population. Okay. And there's your sum of x minus the mean all squared divided by n, where n is the number within the population. In this case here, mu, that's the mean for a population. Okay. This is the one there we'll be using there, okay, the variance there of a sample, okay, and in this case here it's not theta, it's s squared is equal to, again, the sum of the data point minus the mean squared, all divided by n minus 1. And we spoke there last week there, the whole idea that why we use n minus 1 as opposed to n. Right, this is the variance there for a particular population. This is the variance there for a sample that we're going to project on the population. So we have to make this inaccurate in order to project it onto something there that we don't really know about yet. We'll get more as we go. So, calculate the variance of the sample data set. Same data points. Okay, first thing, get them in order, find the mean, right? You input them there into your data table, there are your 5 points, there is your mean. Subtract this one from this one, and remember, it does count. So please just do what it asks you here. X minus mean. In that case there, negative 13. And then you square that negative 13. Now, we just did there with the MAD where we did the absolute value. That's not, I just wanted just to show you that that's how you do the MAD. This is how we do when we solve for standard deviation. This is everything what I'm going to show you guys right here. So you take your minus 13 and you square it. Minus 13 times minus 13 is 169. Minus 3 times squared is positive 9. 2 squared, positive 4, positive 4, positive. And you see the whole point is to get rid of the negatives. Right? It's kind of the same thing as calculating the absolute value, but it works well. And then you sum all of these guys here, 169, 9, 4, 16, 100, and it adds up to be 298. Very important. Okay? You'll notice there won't be any sum values here. The sum value for this one is always 0. And then you sum all of these squared values and you get a number. It's completely meaningless at this point, but we'll get there. Okay, so now you've got your information. Variance is equal to S squared is equal to the sum of x minus x bar squared. That's this one right here. So that value goes right in here on top. And then n minus 1, well, I have 1, 2, 3, 4, 5. 5 minus 1, so that's 4 on the bottom. 298 divided by 4 gives me a variance of 74.5. Therefore, the variance of the sample data is 74.5. What does that mean? At this stage of the game, not much, but it's leading us to where we need to go. Okay, so this is what we call our sample variance. Okay, standard deviation is the most common statistical measure of dispersion and is calculated by taking the square root of the variance. So what we just found, this meaningless number, what was it, 74.5? I don't even know what that means. Doesn't mean anything. Wait a second, we just found the variance, right, Ian? We did. You found the variance for this particular sample size, and the variance in this case here is 74.5. Doesn't mean anything yet. I got to transform that number into standard deviation, and then it starts to sing. Okay? So, you'll notice there, let's go back. Where did that go? Where did my formula go? Why am I not seeing yes? You'll see there, when you're talking variance, you notice there it was theta squared for variance of a population. Variance of a sample was just S squared, right? When you're talking standard deviation, you have to square root. So you'll notice there that that S squared is now gone. The square root of S squared is S. And you'll see there everything under, this was the variance, right? But then we square it, and then that becomes the standard deviation. This is for the sample. This is for the population. Okay. Notice there the formulas are the same as they were up here. Okay. It's just now we're looking for standard deviation, so we have to square root them. Okay. Now, when we get, this is it. Standard deviation, you have to be able to solve for this every single time, because you're going to see there that there's 2 bits of information in statistics that you can't live without. You got to have the mean and you got to have the standard deviation. So you got to be able to solve for the standard deviation. So in this case here, what we just found, you would square root that answer. And then now you've got something usable. So let's square root that. What was that? 70. No, I should go. Where's my square root? There it is. What was that? 74.5. There you go. So in this case here now, we have a standard deviation of 8.6. That actually means something. The variance, you have to do all this work to get the variance, and then at the end you just square root it to get the standard deviation, and that's where everything starts to make sense. How so? Let's have a look here. You have these two different populations. You remember those two populations there from the start, data set A, data set B, that kind of look the same. They both had means of 55, medians of 55. They both had ranges of 90, like by, they kind of all look the same. But if you break things down, you can identify differences, which is what we want in math and science, right? And you have a look here, the smaller standard deviation. So when the standard deviation is smaller, right? There's the first standard deviation, second, and third, right? First standard deviation, second, and third, right? You remember those numbers, 68%, 95%, 99.7, talking about the spread of the data, okay? And you'll see here for this particular graph, as, compared to this one here is much more spread out than this one here. You'll see there that if these were the same scales along the bottom, right, this guy here, the majority of his data falls within this range right here. While for this particular graph, you'll see there that it's stretched out, more variable. So the people in this particular parameter are not thinking as aligned as the people in this graph, okay? The frequency distribution will be narrower for data sets with a smaller standard deviation and wider for sets with a larger standard deviation. Okay? So, let's go back and have a look here. You got these two graphs. You got these two data sets. They look very similar. And in fact, there are a lot of similarities. Let's have a look. So, calculate and compare the sample standard deviations of the two data sets to determine which set has a greater dispersion. Which one is more spread out? So basically what we're going to be doing is you're going to be calculating the standard deviation of this guy. You're going to calculate the standard deviation of this guy, because they both have the same means, right? 55 and 55. And you're going to see what is going on with these two. So, first, calculate the mean of both data sets. 55 and 55. Same mean. Ooh, it's kind of freaking me out. Now, this is the work there. And when we're doing variance, this is where you're going to have to take the time. Okay? You're going to see a chart similar like this there on the quiz that's out. You're going to see a chart very, very similar to this one there for the test, where I will ask you there to compare one data set against another. Okay? So, there's your data values, 10, 33, 34, 35, 10, 33, 34, 35. These are for data set A. And you just put them in order into an array, right? And you do the same thing there for data set B. And they are there as well. Then we calculated the mean, right? The mean would go here. What was that? 55. 10 minus 55 is negative 45. 33 minus 55 is negative 22. And that's the tough part. If there's a negative sign there, you have to keep it. Because I give marks there for filling all these in. I just don't give marks there for the answer. I want to see these charts filled in properly. Okay? Because it does take a little bit of time, and you have to give it its due space. Okay? So you subtract the point from the mean, and you get these values. If you add these all up, they go to 0. This first column here, if you add them all up, they go to 0. Now you take all of these values here and you got to square them to get rid of the negative. Okay? You need a good calculator. Square all these guys, and that's your x minus x bar all squared. And then you sum this total. The sum of x minus x bar, you get, you know what I mean? You might get silly numbers. All of this here doesn't mean anything to anybody at this point in time. You got to take these values here and then go on to the next page. Do the same thing there with data set B. Okay? You can already see what's happening here. This number here is a lot smaller than this number. Interesting. So let's keep going. So you remember that number there, 6728? We just found that, right? 6728, 9250, right? You take that number there, that number, carry it on. So there is your sum. Okay, there's your 9250. Now you got to figure out the variance. So you take this value here to find the variance. And that's your formula, right? Which was s squared. And then you do the square root. In this case here, they just went right to the standard deviation, right? S is equal to the square root of the variance. Plug in your numbers there. There's your 6,728 divided by n minus 1, which is 15. Minus 1 is 14. In this case here, you get a standard deviation of 21.92. Interesting. So what does that mean? The standard deviation is equal to 21.92. So there's the mean. The mean was 55. So go up 21.92. Let's just call it 22. Go up 22. So the first standard deviation would be at 77. 55 and 22. And then 77 plus 22 would be 99. And then 99 plus 22. And then it would go into the reverse, right? This was 55 minus 22, which would be 33. Minus 22, which would be 11. And then minus 22. And you see here, that's how we get these standard deviations. And then you see this one here, we do the calculation, and this one here has a standard deviation of 25.7. Wait a second, this one here had a standard deviation of 21. Right? So the mean was the same, 55, but the distance between the mean and the standard deviation, first one is 22. And then the next distance there between the first standard deviation and second is also 22. So for this particular data value, the standard deviation is 22. Right? That's the distance between the mean and then the next standard deviation and the next standard deviation. In this particular question, we calculated there that the distance between the mean and the first standard deviation is 25.7. Let's call it 26, right? So it would be 26 above the mean and 26 below the mean. And then another 26, and then another 26, right? You see that in this particular case, the standard deviation is equal to 25.26, right? So the space is wider. That means there that this data set, okay, the data points are more widely out there, more variability, less variability, and it's all based on the standard deviation. The smaller the standard deviation, the more tight our population will be. The bigger the standard deviation, there will be more space, more variability. Okay, we'll get more into these there as we go. But that right there, you will most definitely need there for Quiz 2 and Test 2. This whole ability there of, like on a testing situation, I don't think I'd give you 15. That seems like a bit much. I'd definitely maybe 10, 8, somewhere in there. And I would want to see, you know, the mean column. I would want to see the differences in the squared column. Definitely you can't get away from not summing it, because if you sum these there, you got to do that there in order to find the standard deviation. Okay, so have a look at that. Let me know if you guys have any questions. The other measures of variation like range, quartiles, MAD, they have a more obvious interpretation for what they represent. Like a MAD of 5 point, you know, I'm not interested there in interpreting MAD results. The only thing I ask is that you're able there to interpret the standard deviation and what does it mean. Like the standard deviation does not have a simple interpretation. The easiest way to understand the standard deviation is to understand more of its helpful mathematical properties. Okay. Range rule of thumb. This is an easy peasy way to find, the standard deviation when you're only presented with the range. Okay. And please note, this is only a rough approximation and generally will not hold true if the data set has outliers. Okay, this is just kind of a rough way of doing this here. The range rule of thumbs can be used in two ways. There's the formula written like this, where the range is somewhat equal to 4 times the standard deviation. Or you could use it there as a rough calculation to find the standard deviation, which is roughly equal to the range divided by 4. Okay, so to approximate the minimum and maximum values of the typical data in a data set in which we only know the mean and standard deviation. So the minimum value would be the mean minus 2 standard deviations. The maximum value would be the mean plus 2 standard deviations. Okay, here's an example question there. You might see, I think there's a question like this there on the quiz. The average hourly wage for a registered nurse is $36.79 an hour, with a standard deviation of 3.46. Using this information, find the minimum and maximum typical wages for registered nurses. So you have a look here. The mean wage, the average wage of a nurse there is $36.79 an hour. Standard deviation is $3.46. So what does that mean? So there's your mean, $36.79. Okay, well, what are my range? We're trying to find, we only have the mean and the standard deviation. The question is asking for the max and the min. So we need to know the range. Range is equal to 4 times the standard deviation. Well, 4 times 3.46, right, gives us the total range is around 13.84. So 13.84 divided by 2 is 6.92. So that means there's your mean. 50% of the data points are here. So that means there that this is 6.92. 36.79 plus 6.92 gives me a maximal range value, an upper maximum $43.71 an hour. I also have to do it there for the lower 50% of the data. 36.79 minus 6.2 gives us a lower value there of $29.89. And you can see there's your total range, 13.84, which we just calculated. Everything should be there. Have fun with that one. That's using your range rule of thumb. Okay. So the range rule of thumb does provide a quick and convenient relationship between the standard deviation and the range, but it is not very accurate, as it does not take any other factors into consideration, such as shape, size, the data set. And for that there, we need the empirical rule. And we kind of introduced this there last week, and this is everything. This is what we're going to be doing there for the remainder of the course. What I was talking about up here about finding the standard deviation, you remember the first, second, third standard deviation, 68% are in here, 95% are here, 99% are within 3 standard. This is all going to make sense right now. Okay, so we've seen this there before, right? At the all populations generally, if you get enough data points there, will fill in what we call the Gaussian curve, right? It's unimodal, right, where the mean, median, mode are all the same, okay? And we just use the mean here, okay? And in between, like you'll see here, mean plus S, mean plus 2S, mean plus 3S, because this is the distance between the mean and the first standard deviation. And this is the mean in between the mean and the first standard deviation in the negative direction, right? Because if this number is 50, these numbers here are going to be greater than 50. These numbers here are going to be less than 50, right? And so the first standard deviation is all data points that fall within the first standard deviation on the lower half all the way up to the first standard deviation on the upper half. 34%, 34%, so 68% of all data points fall within the first standard deviation. Whatever, and every data set will be different, right? We saw up here that for these guys, the standard deviation was 22 units away from the mean. And we saw for this data set here that the first standard deviation was, 26 units away from the mean. So that is very important, okay, because the standard deviation will differ. Okay, and the tighter the standard deviation, the more closely uniform everyone is acting like within your sample. People are thinking alike. The more spread out your standard deviation is, the more variability there is. So you'll see that 68% of the population lives within the first standard deviation, about the mean. 95% of the population exists within the second standard deviation. And the second standard deviation, see that distance there? What was that for this one here? What was it? 21.92. Let's say 22, right? So, right, whatever your mean is, subtract 22, and whatever that number is there, subtract 22 again, and that's the boundary there for the second standard deviation. And again, on the other side, right, I would add 22, add 22, and whatever that number is there. So 95% of the total population falls within 2 standard deviations, and 99.7% of the population exists within 3 standard deviations. Okay, this is what we call the empirical rule. Crazy important. Okay, very important. Good. Good. Let's leave that there. All right, so the empirical rule allows more precise information to be drawn about the distribution and the percent of the data that falls within certain intervals around the mean. These are called standard deviations. That's everything, which indicates there the spread of the data. However, it only works for distributions that are symmetrical and roughly bell curved, such as these ones here that we've been looking at. We call this there the normal curve. Okay, and I don't know if it was said to you there earlier, where did we get these percentages from, right? 68%, 34 and 34, 95% under 2 standard deviations, 3 standard deviations encompasses 99.7. It's all the area under the curve. So that area under the curve is 34% of the total area under the curve, and both of these would be 68%. So it's all about area under the curve. And now you have a look at this graph right here. It has a mean of 68, right? With a standard deviation of 9, right? So I add 9, add 9, add 9. And there's my first, second, third standard deviation. We don't go into 4th, 5th, 6th because we only do 3 standard deviations, so that is the limit. Okay? Standard deviation was 9, so 68 minus 9, 58. Sorry, 59 minus 9 is 50. Minus 9 is 41. And then that's where we stop. We have our 3 standard deviations on this side, 3 standard deviations on this side. We now have a good curve. Now, you'll see there that where do we get this graph? And it all comes from this. It's a standardized normal distribution. This is, remember I talked to you guys there at the start of the course, the ability there to compare apples and oranges. That, you know what I mean, we've heard our whole lives there that we can't compare. Well, what if I did a study here and measured there the amount of apples eaten? And then I did another study there, and where I measure oranges eaten or whatever. It doesn't matter. what you do is, you have your graph here, you have your mean, you have your own standard deviation, and then for your other bits of information there, your other data sets there, they have their own mean. They have their own standard deviation. Well, what you can do is you can transform these guys into what we call a standard normal curve. And you'll see there that now I have a mean of 0 and first standard deviation, second standard deviation, third, and again there in the negative, right? And 34%, 68%, nothing's changed. 95%, 99 point, nothing's changed. But now I have a mean of 0 and standard deviations of 1, 2, 3. Well, now if I take my oranges and my apples and I transform both of these into standard normal curves, then they'll both have the same mean, they'll have standard deviations, and we'll be able to look at them, right? Comparing apples and oranges. And that's where we're eventually getting to, okay? Look at all of the info we get from only having the mean and standard deviation of a population or sample. Since we know that the mean is 68 and the standard deviation is 9, that's all the information I'm giving in this particular question. Look at all the information you can get. Standard deviation, okay, of 9. You got a mean there of 68. Now you can see everything from only these 2 bits of information. That's why you got to be able to get the mean. That's why you got to be able to get the variance and then take the square root of the variance. You got to be able to get that standard deviation because this is the direction there that we're going. Okay. All right. So in a college statistics class, the mean final exam mark is typically 68 with a standard deviation of 9. Oh, boy, those numbers sound familiar. Use the empirical rule and below diagram to answer the following questions for a statistics class of 200 students. How many students are expected to score between 59 and 77? How many students are expected to pass the exam, get over 50? What mark would the top 5 students in the class be expected to score above? Okay, so you have a look here. I've got a mean of 68 and a standard deviation of 9. So there's my graph. Mean of 68 plus 9, plus 9, plus 9. That's 34%, right? Minus 9, minus 9, minus 9. There's my first standard deviation, second standard deviation, third deviation. It's all based on, that. So how many students are expected to score between 59 and 77 on a test? Well, it just so happens there that there's a mark of 59 and there's a mark of 77. Oh, those fall right on the first and second standard or first positive and negative standard deviation. So I already know the percentages. How many students? Well, 68% of the students are able to do that. You have a look here, right? So how many students are expected to score between 59 and 77? 68% of 200 students, right? Because there was that's from the original question. So 0.68 times 200 gives us 136 students are predicted to score between 59 and 77. Okay. Question number 2, how many students are expected to pass the exam? So where is pass? These are my real marks, right? Down here, right? That's my mean, 68. That's the average score, 59. Oh, there's 50%. So that's a pass. So that means there that everybody to the right passed. Everybody to the left, because their scores are lower, they failed. So the question is asking how many students are expected to pass. So I want to know how many students are over here, right? And you have a look. There's a couple of different ways you can do this, okay? You can just go, well, all of this information from here, third standard deviation on this side to the third standard deviation on this side is 99.7. But no, we only go to the second standard deviation on the left side. So Here, all of this on the right side here, 50% of the data value. There's 50%. Plus 84 is 84. Plus 13 and a half, 94, 97.5. Okay. So 97.5% of the people are expected to pass. Okay. As well, you could look at it like this, right? You look at the opposite here, and this is this stretch of the graph, which corresponds to this stretch right here. That's 2.35%, right? Subtract that from 100, right? Right here, right? 2.5 minus 100 is 97.5. Different ways to do this. However you want to do it, just get the right answer. Okay, so that's just another way to do question number 2. Question number 3 here. What mark would the top 5 students in the class be expected to score above? So top 5 students. Well, first we need to calculate what percent of the data 5 students represents. So 5 students divided by 200 students times, so 5% of the 5 students represents 2.5% of the total. And what would their marks be? Well, you have a look here. Go to the top 2, right? Because these guys here have the highest marks. These guys here have the lowest marks. Why? Because our grades are increasing. Higher numbers are on the right. Lower numbers are on the left. I'm looking for the top 2.5%. Well, you have a look here. There's the lower 2.5. Here's the upper 2.5. So I would expect there the students would get a score of 86 or above. Okay. Here's some more questions there. Given the following information from a sample data set, calculate the variance and standard deviation. There are the answers. Try, you know what I mean. Try it out. See if you can get the same answer. If you get the same answer for the first one, don't bother doing the second one. Just extra questions there. Practice, practice, practice. Okay. We've got this one as well, and just letting you know there that we have arrived. That concludes all information there for test 2. Okay. And then after test 2, we are going to continue on with this stuff. Okay. I wish you guys all the best. Let me know if you guys have any issues. Your assignment 2 is live. Your quiz 2 is also live. And it's all great preparation there for next week's test. Next week's test will open up there Thursday. You'll have, 5 or 6 days to do it. So there's no rush. I'm really pulling for you guys. Take care. Have a wonderful day. And let me know if you guys need anything. Okay? Take care and be well.